Hello, good morning. How's everyone doing today? This is our last class for the semester. And any questions about the upcoming exam? It's going to be available on Canvas. If you go to modules and go to scroll down to the last module, you'll see final exam made available Friday next week. So next week is the all finals week, and Friday is according to university's schedule, that's going to be the exam for this class. So you can access it any time during those 24-hour period, and the final will be 25 questions, and that will be 3 hours. So you have 1 extra hour than the midterms. Okay. 25 questions and 3 hours. So 3 of those questions will be long calculations, and the rest of the questions will be multiple choice. Okay. Any questions on that? Okay, if you do think of any questions, feel free to email me anytime between now and then. Next week, I will host regular office hours, Monday, Wednesday, at the usual time, 2:30 to 3:30. So if you have any questions when you are preparing and studying for the final, feel free to stop by the office hours. And of course, you can always email if you cannot make to those times. All right, so we have one last topic left. We have dealt with, oh, there was one question. There's a question in the chat here. How many points will the final be? It will be 70 points. So total of 70 points with the longer problems where you could upload your solution count for roughly 30 points. And the multiple choice is 2 points each. Okay, so our last topic is fluid dynamics, right? So so far we've been talking about fluids staying still, but now fluid starts moving, they're flowing. So we're going to investigate flowing fluids. And just want to say that our hypothesis is we consider ideal fluids. What do we mean by ideal fluids? That they're incompressible, okay, it cannot be compressed. And that is a good assumption for liquids, not so much for gases. They're not viscous, so there's no kinetic friction between the liquid part. All the flow we investigate is steady flow. So what I mean by steady flow is that they don't have laminar flow. There's no turbulence. There are 2 principles we will learn that we can use for fluid dynamics, flowing fluids. The very first one is a continuity equation. A continuity equation here is really just a conservation of mass. When you study, when you take 1520, the ENM, you'll have a continuity equation that study the conservation of charges, which tell you about the flow of the currents. Here, we're talking about the flow of a liquid, for example, water. So consider if you have water flowing through a tube, we imagine the paths are taken by the water particles in the fluid, and we can visualize these paths by drawing some streamlines, something like that. If we're talking about ideal fluids, then these streamlines have 2 important properties. One of them is that these streamlines do not cross, because we said that these are laminar flows. They don't have turbulence, so the streamline never cross. And when you have streamlines more closely together, they indicate higher speed. Okay. So what do we mean by continuity equation is the equal amount of time, you have equal amount of fluid coming in and going out. So giving you a really easy example is the continuity or the conservation of human counts. For example, there is a lobby and there's always 10 people in the lobby. So there is a steady flow of people throughout the lobby. If you have 5 more people coming into the lobby, then you have 5 people going away from the lobby, remaining 10 people at all times. So that is basically a conservation of human counts, just to show that the number of people in the lobby never accumulate to be more or never decrease to be less. It's keeping the steady flow. So this is the last slide.
Sorry, just to clarify. So it's like a capacity, like a maximum capacity?
It's not a maximum capacity for the continuity equation. It doesn't have to reach maximum capacity. It's just saying that we're talking about a steady situation. So when something is steady, there is no change, meaning that if you have 10 people here at one instant, and then the next instant you look at it, it's still 10 people. If people are increasing, right, you get more and more people coming in than the people leaving, then you will see, oh, right now I look at it's 10 people. Later on, I look at it, it's 12 people. So that's not a steady flow. Does that make sense? So if water flowing through this pipe for a steady flow, then we can see that from the cross section 1, you have some liquid coming in. Cross section 2, you have some liquid going out. Whatever comes in is equal to whatever goes out, because that's a steady flow, right? It's not like you block 2 and the water only come in, never leave out, right? Or if block 1, you let water only go out without coming in. This is a steady flow. So we were looking at, okay, we're saying the liquid going through point 1 and 2 should be the same. So how to represent the liquid that going through point 1 and 2? Okay, so we can calculate the liquid by looking at the volume of the liquid, right? How much volume of water is coming in at points 1. So we're saying, okay, if the water is flowing with the speed velocity v, then during time delta t, it would have gone by a distance of velocity times time. So v times delta t, that's the distance, the volume of that particular water has traveled by. So you can imagine this cylinder block of water that whatever came in during those time dt period. So how do we calculate this volume? This is a cylinder, right? So we know the height, which is the distance it traveled. We know the cross section, which is how wide the cross section is at point 1. So it's A1. Multiply the area by the height, you get the volume. And you could do the same thing for the volume of water the passing by point 2 at the same amount of time. You use a different cross section and a different time. Okay, so you realize whatever goes in goes out. These two volumes has to be equal to each other. They're all passing by in the same amount of time delta t. So you cancel delta t. You get a continuity equation is A1 V1 is equal to A2 V2. So this equation tells us when you have a wider cross section like A1, then the water is flowing slower. So A1 is bigger than A2, which means V1 is smaller than V2 because A1 V1 multiplied together is equal to A2 V2. So that also makes sense, right? Because if you need to pass by this much water in the same amount of time, but 2 is much more narrow. So you just need to move this water faster so that equal amount of water could pass by. So the water has to flow faster at narrower pipes. Just like if you are trying to keep up with the steady flow of people, but then all of a sudden that your road gets more narrow. So in order to keep up that pace, you need people who are narrower to walk faster so you can get people out of the way with still same amount of people out of the way in the same amount of time. Okay, so that is a continuity equation. Simply saying whatever goes in must come out you have a steady flow and fluid is not created or lost inside, because in equal amount of time you see, oh, this much come in, but if not that much also come out, then what does that mean? Meaning that, well, some of the fluid are lost inside, or if you have more liquid coming out, you might wonder some of the fluid has been created inside the pipe. That just doesn't make sense, right? So it's really simply a idea of conservation of mass. And in the application of 1520, you will have a continuity equation you can write for, instead of water currents, you have electric currents, and you have a conservation of charge. But you will see that in 1520. Okay, a quick application of that A1 V1 equals A2 V2 is this bridge question you have just done. You have a water flowing through a pipe in the middle, is much narrower than on the two sides. In the middle, you have a constriction. So how does the speed of the water in the constriction area compare to the rest of the pipe? We had said, well, whenever your area is narrower, your velocity has to be bigger. So in the middle, you have to flow faster. So the answer A is correct. Okay, now let's try to use that equation in the quantitative way. We have a hose, the diameter is 4 centimeters. If you want the velocity of the water to come out to be 4 times bigger, then what do you want your diameter to your nozzle to be? Okay, so if you want water to be faster, you probably need to reduce your cross section, and exactly just how much do you need to reduce it? Bearing in mind the continuity equation we will use to answer this question is A1 V1 is equal to A2 V2. Okay, all right, so this I will go ahead and open up the vote for you guys. Whenever you're ready, you can put in your answer.
All right, take care.
All right, so I gathered majority of your votes. Let's run for another 10 seconds. Okay, all right, so let's go ahead and close this. We'll take a look at our results. Okay, looks like the majority of the answers are A and C, with C being 2 centimeters and A is 1/4 centimeters. Okay, so it looks like there is a ratio, 1/4, 1/4 is a ratio that is important here, right? If your velocity is 4 times bigger, then your cross section has to be 1/4 of your cross section of before. Do you agree with that? Okay, all right, so if we agree with that, how do you need to reduce your diameter so your cross section, the area of the hose is 1/4 of what you had? Knowing that,
This
go ahead, sorry.
in this question, I think you need to cut the diameter in half because the area would be pi r squared. And if the radius is 2 centimeters, then you're going to get 4 pi as the area. And then if your radius is 1 centimeter, you're going to get 1 pi as the area, which is 1/4. So
Yes.
probably a diameter of 2.
Yes, very good, Grant. The question is asking the diameter, and since the area is the radius squared, which will be diameter over 2 squared, so you need to reduce the diameter by half. So that 1/4 talks about the ratio of your area, but that's not the ratio for your diameter. So a half of the diameter we need to be 2 centimeters. So the details is written here, but we basically have already talked about it. So 2 centimeters will be what you want for your hose. Now the second principle, other than continuity equation, is called Bernoulli's equation or Bernoulli's principle. That really is another way of using conservation of energy in terms of fluid flow. Okay, so we will go through this derivation together. So recall our general conservation of energy. What does that look like? The final energy minus initial energy is equal to the energy input minus output, right? The input and output are your energy transfer, which is done through some external forces doing work. So here, if we're talking about water flow, we have, yes, water is flowing. So we have kinetic energy. And water here or there could be at different height because sometimes water goes up or down, then you will have different potential energy, right? So that could be your final and initial energy. And that change is your energy transfer, which is calculated by work done. So let's first consider how do we calculate the work done. If we look at 2 equal volumes of water entering and leaving a tube. So because of the water pressure, right, when it's entered, it's being pushed on by that pressure. So there is some force pushing these water into the pipe. And that is your energy input. Coming out, you can see the pressure on the other side is pushing in. And that will be your energy output. So pressure from the left-hand side, P1 is pressing to the right-hand side, and P2 is pointing to the left-hand side, right? Because we know that pressure is coming from all around. So if you look at this cross-section, from this side, pressure is all around. So all around, right, in all different directions. So from this side is to the right, from this side is to the left. And because our water is flowing to the right, making the force associated with P1 will do positive work because, okay, the force here is pressure times area, right? So the force is P1A1, and that force will do positive work because your displacement is also to the right because your water is moving to the right. So that energy input, we will write it using force times displacement. So force is P1A1, pressure times area. Displacement is distance D1. And you can see if you combine A1, D1 to be volume, you get P1 volume. So that is your energy input. That is the amount of work done from the left-hand side of the pressure force. You do the same thing for the right-hand side, but knowing that the force is to the left, but your displacement is to the right. So you will get a negative work, right? So negative P2A2 times displacement D2 you combine area and distance together, you get a volume. So energy output is P2 times V. So overall energy transfer is P1 volume minus P2 times volume. So that's what we have for the energy transfer. Then we have to deal with the potential energy and kinetic energy. So which means we have to write our expand our energy initial and final using the kinetic energy and the potential energy terms. Okay, so we will walk through the derivation together, but knowing that when we solve a problem, we will just grab the final results and we don't have to do the derivation again. Okay, so in the case where your water does go up or down, it's not a level where you're flowing on the same level, then you certainly don't have to consider gravitational potential energy. But if your water does go up and down, then you need to consider the gravitational potential energy, which is mgh. Here we will use y to represent that vertical height. For this particular volume of water we're looking at, that's volume V, the mass for this volume. So mgh, the first variable is the mass. So we can represent mass using density times the volume. So which means at these two different height, you have two different potential energy, right? One of them being m1gy1, one of them is being m2gy2. So you realize we're talking about the same body of water flowing. So the mass is the same. Which is all density times volume. So the density is the same, volume is the same. The only difference is the height, y1 or y2. And pay a little attention on where did we draw our height. So at point A1, why do we put our height y1 right there? And why do we put our y2 right there? Why didn't we move y1 higher or lower? Why does it have to be exactly at that location?
Is it the center of mass of the fluid in the pipe?
Oh, yes, very good. Excellent. That's very good. Yes, exactly. This is continuity. This is a homogeneous liquid. When you are talking about a continuous distribution, we viewing that all the gravity is acting concentrated at the center of the mass. So we need to use the average position to represent the overall height. You can see some of that water is above this height, some of the water is below this height. So we just choose whichever the center of the mass is. So we draw the height right in the middle. Okay, so now we have our potential energy. The last piece of the derivation will be the kinetic energy. Kinetic energy is 1/2 mv squared. Knowing that, well, didn't we just write out our m, mass, which is density times volume? So we can just write 1/2 rho times v times velocity at point 1 squared versus velocity at 2 squared. So the kinetic energy, like potential, the mass part is the same. The only difference is the speed of the water at location 1 might be different from the speed of the water at location 2. So velocity is different. Here we have two different V's we're using. The capital V represent volume. The little v, lowercase v represent your speed. So we wanted to differentiate by using one of them using capital letters, one is lowercase, so we know which one is which. Now we finally have all our components, we can combine them together. So we will soon have our derivation. Okay, so energy transfer, right, is P1 volume minus P2 volume. We got that from looking at the work done by the forces. Gravitational potential energy is mgh. M is represented by rho times volume, and the h is height, y1 versus y2. Kinetic energy is 1/2 m times velocity 1 squared or velocity 2 squared. and plugging into the conservation of energy equation. We will also cancel out all the terms we can. For example, the volume V is the same everywhere, so we can cancel that. Okay. We can also rearrange things a little bit, moving all the ones to the left-hand side and all the 2 terms to the right-hand side. So there we have our Bernoulli's equation. So let's look at what it says. It says P1, the pressure at one point, plus 1/2 density of whatever is flowing, if it's water, is density of the water, times the velocity at that point squared, plus density times g times the height of the water at that point, is equal to pressure at a different point, plus 1/2 v rho velocity square at another point, plus rho times g times your height at a different point. So this is really just a restatement of conservation of energy. So the 2 principles we had talked about here, one is continuity equation, one is Bernoulli's equation, are really just a restatement of conservation laws. We said conservation laws are so fundamental and important in physics. So the continuity equation comes from conservation of mass. Here, the mass, our mass being the mass of the water. Bernoulli's equations come from conservation of energy. Okay, so what I want from our students is to, by learning physics, when you eventually see these equations somewhere else, maybe in the engineering setting, you can be reminded of the physics behind these principles are really just the mechanism of conservation laws. Okay, so we have our 2 principles. Now let's use them to try to answer some questions. The first one is a continuation of the bridge question we just answered. So the first bridge question asks, what is the speed in the middle, right? So we're saying, okay, A1, V1 is equal to A2, V2. So whichever area is smaller, velocity is bigger. So we know that right in the middle, water flowing faster. Now, the next question is, how does the pressure of the water compare in the middle versus out in the more wide area? Well, to answer pressure question, we have to use Bernoulli's equation. Seeing that the fluids is at the same height, right? So there's no difference in the y's. So let me go take a look at our Bernoulli's equation. So rho gy1 and rho gy2, these 2 terms are now the same. You can cancel that. So you end up with pressure plus 1/2 density velocity squared has to be a constant value. So whichever velocity is bigger, your pressure will be smaller because they add up to be the same, right? So if we know that the water is flowing faster in the middle, which means the pressure must be smaller according to Bernoulli's equation. So it is smaller would be the correct answer for the second part of this question. A lot of times we do have to combine continuity equation and Bernoulli's equation to answer some problems. But now we just go into the following of a couple of questions will be focused on just Bernoulli's equation. Let's take a look at this question together. So if you poke a hole in the container, you can put it at 3 different locations, point A, point B, and point C. Point C, which point do you think the water will come out faster? Okay, so I will give you a hint that we are using Bernoulli's equation to try to answer this question. Okay, so take a moment to think that when you're ready, you can put in your All right, so let's wait for 10 more seconds. If you have last minute vote, please put it in at this point. All right, okay, so let's go ahead and close it. We'll take a look at the results. All right, yes, so the bottom one, the number C, get the most choice. It's the rest of the two, A and B, are pretty much tied. I think it would be intuitive to think the bottom one will flow out faster, but how do we put that into using the physics to justify our choices? Anybody would like to give some thoughts? Or if you like to talk about the reasoning for possible choosing A or B, that's also welcome.
If you chose A, it may have been because like at point 8, it has the most height, so it'll have the greatest potential energy. And since, at least how I interpreted the question, I believe we're trying to like get it so that velocity gets maximized at the end. Basically that, potential energy does have more to help contribute towards velocity in terms of energy. That, and then also someone who chose A could have thought about how there is still some pressure from water, have some initial pressure, but C has like not much, so it might be because of that. And I think
C has
C
not
or A,
much of what?
sorry, what?
So you said C may not have as much.
Oh
So
yeah, C. So
as
C
much
doesn't
of what quantity then?
potential energy,
Oh, potential energy.
but it has more initial pressure because it's further down in the water. So I think like if this were like a test, narrowing it to A or C would probably be easiest.
Very good. So it looks like you have talked about some really important elements here. That is, the potential energy might be involved, and also the pressure at different locations might be involved. So you can see that, yes, you have, before we punch any holes, we have hydrostatic pressure at A, B, C, and obviously at point C, you have the biggest hydrostatic pressure because it's a greater depth. But once we punch holes, you can see right at that point, what is the pressure? Pressure, you can see that point after you punch a hole, it's in contact with the atmosphere. So wherever you have a contact with the atmosphere, your pressure at that point have become an atmosphere pressure. Right, so point A, B, C will all have the same pressure, which is the atmosphere pressure. And we also you talked about potential energy. So how does that all fit in? If we use Bernoulli's principle, we can see the one side of the equation has three terms: pressure, potential energy, and the 1/2 density velocity square. So let's just put the the equation out and see what happens. So if we list the Bernoulli's principle for two different points, now these two different points could be between A and B, or B and C, or versus A and C. They all have the same pressure, which is atmosphere, because you punched the hole, right? You can get rid of the P terms, and what's left over is the potential energy term and the velocity squared term. Where at point C, you have the smallest potential energy, that's versus smallest y, which means the velocity there would have been the biggest. Okay, so because you can see gy1 plus 1/2 v squared is equal to gy2 at 1/2 v squared. So if y1 is the smallest, meaning that the v1 would have to be the biggest. So among these three different holes that you have punched, then C has the smallest y, will give you a fastest speed. So using Bernoulli's equation, we were able to answer this question in a more rigorous way. So yes, hole C is correct, the fastest coming out. Now let's look at a different question, which might be very similar, okay? But the difference is we punch 2 holes, right, on the bucket. However, the ones that come out from the top, you added the holes, added the pipe, okay? So one is on top coming out with the pipe and bent downward. So make sure that it's flowing downward. And the other one is right at the bottom of the bucket. So in these 2 scenarios, if we're looking at the water speed coming out, which one give you a higher speed? It's coming from the hole, which is choice A. That is the one in the bottom, or the pipe, which is connected to a hole on the top, or is it the same? So I'll give you some time to think, and then when you're ready, we could put in our vote. All right, so it looks like we gathered majority of the vote, just 10 more seconds and we can wrap up. Okay, all right, so I'm gonna go ahead and end this. We'll take a look. It looks like we are pretty much tied among these different answer choices. Yes, so let's hear some different thoughts. Preferably thoughts for each of the choice. Anybody would like to share their thoughts with us?
Sorry, I missed it. Did you ask like our reasoning for which one we picked, or
any kind of choices?
Oh, okay. So I think that personally I picked the same because I kind of used the logic we used last time, and I said that so they're coming out at the same. So even though the pipe, like the little, the pipe is higher up, the height that the water comes out is actually the same for both, and they both had the same pressure because it was the atmospheric pressure, and I'm just assuming that they've got the same, cross-sectional area and stuff. But so they're coming out at the same height, so that means their potential energy is the same. They have the same initial atmospheric pressure. So that means that when we solve for everything, that velocity should be the same for both of them. At least that's what I think.
Yes, very good. By attaching a pipe, and where are we looking at observing the water? So we're not really observing the water right here when it's first enter into the pipe. If we were, we would say yes. The bottom one would have a faster speed than the top one. However, by connecting this pipe, we are looking at our water coming out here at the bottom. So which make them have the same height at this point. Right? They're all coming out at Y1. And they're all in contact with atmosphere. So P is also the same, which will give them the same speed. So in this case will be C is correct. And again, you can see that is simply a direct application of Bernoulli's principle. The fluid flow, the fluid dynamics, when fluid starts flowing, we have two equations we talked about today. One is a continuity equation, which is really a conservation of mass. Mass cannot be created or destroyed, right? So whatever comes in must also go out. Bernoulli's equation is a conservation of energy. So a lot of times problems could require both of these combined to answer that question. So we'll take a look at such a question. So here is a bridge question we've already done. Now we're giving a water flowing in the pipe. Now you can see two things that's different. One is the height is different, right? Water is lower here and then go up higher. And also the cross section is different. Left-hand side is narrower, right-hand side is wider. And given the particular relationship between these two pipes is the pipe is twice as high. So this is twice as high and 4 times the area. So the area is 4 times. Given these two relationships, will we be able to find out the relationship between the pressure at the left-hand side and the pressure on the right-hand side? So the first thought would be, okay, let's use Bernoulli's equation, which talk about the pressure, right? So you can see, okay, we want to compare pressure from the left-hand side to the pressure on the right-hand side. Then you can see, okay, well, then that depends on the height, and the height, this height is 2 times of the height on the left-hand side. So H right is 2 times HL. But you can also need to decide, okay, how does the velocity compare? Right, velocity on the left-hand side versus the right-hand side. You realize, wow, it looks like I also need to combine this with continuity equation to get the relationship with velocities and then combine it with Bernoulli's equation to finally figure out how the pressure related. Okay, well, I realized, okay, I know how velocity are comparing because A1 V1 is equal to A2 V2. In this case is A left V left is equal to A right V right. So if the area on the right-hand side is 4 times as much, then we know that the velocity on the right-hand side is 1/4 of the velocity on the left-hand side. So here we got the relationship between the height, we got the relationship between the velocity, we can plug it in, and we can figure out the relationship of the pressure. So we do that, plug in this and this, okay? And you can see by moving things around and doing a little bit algebra and cleaning things up, eventually you get the pressure difference between the left-hand side and the right-hand side of the pipe is this equation. It doesn't look like a simple relationship because it does depend on what the height is. It also kind of depends, on what the velocity is. So how much they differ really depends. So the answer would not be either of those simple choices. It really just depends on the speed of the flow and the height of the flow. So we'll have to choose D. You can see this is an example of combining Bernoulli's equation and the continuity equation. One last little thing before we go is there is great applications of these principles. Of fluid dynamics is one major area of study for especially aerospace engineering or any type of engineering where, for example, if you're dealing with designing of cars, shape of the cars or the airplanes, we could use Bernoulli's principle to explain why they are shaped in such a way. We can call they're streamline shaped, but why would this kind of shape helps? So it turns out by having this shape design, we're creating a difference in terms of how the air will flow through. Sorry, did I lose my? Okay. So we're by having the streamlined shape, right? The air flowing through the top of the wing and the bottom of the wing. By having this curvature, we make using we created a pressure gradient so that air on the top move faster. So the velocity moving faster reduce the pressure because Bernoulli's principle saying pressure term plus 1/2 velocity squared term is a constant, right? So wherever your velocity is higher, your pressure is lower. So the pressure on the top of the wing is smaller compared to the pressure on the bottom of the wing. So here you're giving yourself and you're creating a lift so that the force on the bottom is bigger than the force on the top. So it's easy for the object to stay afloat. Because of that, less force on that side. There is also another application that we can use Bernoulli's principle to explain why you can sort of trap a ball using a leaf blower or a hair blower. That you have a stream of air, you can put the ball in the middle, you can pretty much move it relatively large range without the ball falling. So let's take a demo of that particular scenario because that one is hard for us to imagine. Okay, so let's go ahead and proceed. Whoops. Oh.
My job is to make college easier because students have a lot on their
Sorry, coach.
plates. Mike Harper, an econ major who
Home in West Virginia had a heat vent balloon, and the balloon was balancing in midair above that heat vent. And I thought, how in the world does that work? And it's actually quite interesting. So this is the phenomenon. We've got a stream of air that comes up vertically in the case of West Virginia through the heat vent. And then you've got a rather light object, in that case a balloon, in this case a foam ball, that's perched and being balanced and levitated by that stream of air. The principle is that the uprushing air holds the ball up. There's some momentum transfer when the air hits the bottom of the ball and it holds it up. So that part is not so mysterious. The part that is mysterious and was to me was what happens if that ball gets off-centered? So let's say it moves to the left.
So the key of this is, okay, we have a stream of air supporting a ball. Well, that's not, well, of course, you have that air blowing it up. So what's so fancy about that? The interesting part that you can move the ball relatively off center and it gets sucked back into the stream of air. It's like you're making an air trap. The ball is not easily moving away or being disturbed. So look at the diagram here on the right-hand side. If the ball is really off center where you're blowing the air from the right-hand side, the left-hand side is just a regular atmosphere, right? So the air that you're blowing, moving with a higher speed, so that Bernoulli's principle saying, well, if air moving with faster V have a lower pressure P. So the left-hand side of the ball is just the atmosphere. smaller velocity with a higher pressure. So the force on the left-hand side will be bigger than the force from the right-hand side, basically pushing the ball back into the center. So you're creating a trap. So whenever the ball is deviated from the center, you get pushed back in. So that's what we're talking about of trapping the ball with a leaf blower. So it's much more obvious when he finally do this with a much bigger object. So let's take a quick look at that.
Including this rather large scale demonstration.
You can see it quite steady, it doesn't fall away easily, even if you can make it tilt. All right, so that is one other phenomenon we can use Bernoulli's principle to experiment. So that's all we have for today. We had talked about continuity equation and Bernoulli's equation. That concludes our discussion for the fluids and also the semester. All right, thank you everyone for all of you who stay with us and come every Monday, Wednesday, Friday, every week for our synchronous meeting. And I wish you a good finals week and a good winter break. Bye, everyone.
Bye, Professor. Thank you. Have a good break.
Bye-bye.
See you later.
See you. If you guys have any questions from between now and later, just email me.
Thank you so much, Professor. Have a nice winter break.
Bye, and you too.
Bye, Professor. Take care.
Oh, bye-bye. Yes, thank you. Take care. I'll see you on office hour next week.
Yeah.
I will. I think I still have an email I need to get back to you. I work on that today.
Okay. Thank
Okay.
you. Appreciate
Bye-bye.
it. Okay. Bye-bye.
Bye-bye.